Okay. So this week we are going to see topics on frequency response analysis, week 7 contents. Before that, somebody has raised question about that surprise test, right? So I checked with the team and with the faculty member, and they are telling that it's not mandatory to take surprise test in each and every week. As it is surprise, we can take it at any time. That's what the whole point of doing that. So you don't have to worry about it. Just keep performing better in your surprise tests. We will take an average of those things later, and that weightage will be decided later. So we will let you know once everything is bundled together after week 12, right? So you don't need to worry about like, why the week 2 doesn't have a surprise test. We may or may not have in every weeks. So we may ask you to write a test by surprise, right? So there's no problem in that aspect, right? So I hope you have some knowledge about the topics we have seen so far until week 6. That week 6 is really important topic, RH criterion and also the root locus. And I hope you are good in that concept. And please, if you have still if you have some doubt or you're not sure that if you can solve a problem right away, please solve some example problems. Go to the reference books, solve problems first, and take some practice problem from the exercise and solve it by yourself. There are many solutions, PDFs, and everything is available online. So please make use of it before going to the end semester. Okay. Sorry, quiz two. So
Hello,
yeah.
ma'am. Can you suggest me some reference books?
Ah,
Actually, in the portal there is no reference book.
mm, it is supposed to be there. Why it is not there? Maybe in week 0 it is there, I think. Let me check it quickly. Non-swimming course basis. Course orientation. Okay, fine. About the course is also not there. Okay, it is there. If you go to your course introduction, in that there is a sub category about the course. In that about the course, to know more about the course, please click on this link. There is a page, ES course page. If you go there, you will get this prescribed books. There are 4 books mentioned in that website. Modern Control Engineering by Ogata, Feedback Control of Dynamic Systems by Jean Franklin, Mathematical Modeling of Physical Systems, and Introduction by Basma Dijan, Control System Design by Friedland. So, out of this, the top 2 are the best. I cannot say best, but it has more relevant examples as we do in our course. And the third one has more example relevant to your week 1, like modeling, how to model a system, physical system, electrical, mechanical, everything. And fourth, you can complete the first 3 and then you can go for further information to the fourth reference book.
Okay, okay.
Most probably try to focus in the modern control engineering or what. You will get all the information related to our course in the first book itself. Okay,
Okay.
fine. Uh,
Ma'am, I have a doubt on GA
uh-huh.
week 6. I I posted questions in discourse
Uh,
and you responded.
uh,
But I actually
uh,
doubt, ma'am. You said that see. First, the question week number 6, GA, question number 5, sir.
Okay. Week 6, GA, question number 5. Let me open it.
Hmm.
I don't remember that. We'll do this quickly because I have a lot to cover. Yeah, fifth question. True or false question, right?
Yeah, ma'am.
Ah.
Ma'am, here is said the system is stable for all values of k.
Uh-huh.
So, and he told that we checked only for k is greater than 0.
Yes.
So, how to know the k greater than 0? Actually, here is said all values of, so negative and positive, all values.
No, no. In this case, wait, let me show it to you. In root locus example, as you, this is based on root locus, right?
Yeah.
So in root locus, what you used to see is root locus itself is defined as a graph for all possible roots of the characteristic equation 1 plus k L of s or g of s, whatever. L of s is loop transfer function, or in general, we will take g of s, right? As parameter k varies from 0 to infinity. This is how the root locus itself is being defined. So you are tracing the locus of the roots of the characteristic equation while you are varying a k. For example, if this is your system, for a pole at a minus a, s plus a means here minus a, right? So by varying this k from 0 to infinity, how your locus will change. That's what this root locus tells you. Maybe it change from here to here, right? Root locus occurs in pair. So it might change from here to here based on your nature of your system. So what this will tell at every values of k from 0 to infinity, how your locus will vary, right? So here itself you are considering 0 to infinity. In a problem that asks with a continuation of a root locus problem, always the k is assumed to be greater than or equal to 0, because if the k is less than 0, if you consider, it will be minus k by s plus a. Then if this is your root locus for actual system, for example, if this is your root locus for a k by s plus a system, this will be inverted. This will be the root locus for your minus k by s plus a, and it entirely change the properties of the system, because your locus will should be seen from the right of that mm, what do you say, a locus will be traced in the right of your poles. For
Hmm.
example, how do you trace a root locus? If there is a, if you will take a test points and you will see if there are odd number of poles or zeros in the right side, you will consider that inside the root locus, otherwise not. So if you take this test point, there are no roots again in the right hand side, though you won't consider. But if you take this as a test point, there is a one odd root, odd poles, so we will consider this as a inside the root locus. But for minus k by s plus a, this is inverse. So you will check the left of that. So if you check in the left of that, if you take this test point, this will come inside the root locus. They entirely change the plot of the problem, right? So always in root locus problem, k will be considered greater than 0 unless and otherwise it is mentioned to be the other way around.
Ma'am, if we consider left side, then
Mm.
it's unstable.
But I haven't heard after half.
Actually, when here is minus k upon
Mm.
s plus a,
Mm.
so we consider left side.
Mm.
So if we consider left side, then
Mm.
it's unstable.
Consider left side. After that, what did you say?
Uh, Ma'am, how to when we say k greater than 0,
Mm-hmm.
so we consider right side for plus k.
Mm. There are two ways of root locus. Okay, one root locus is you are tracing by varying k from 0 to infinity.
Mm-hmm.
This side. This is one root locus. This we usually do. This is a normal way. We call this as positive root locus. The negative root locus is the other way around by changing from minus infinity to zero. So 0 is 0 to infinity, here minus infinity to 0. So unless and otherwise it was mentioned the other way around with negative root locus or something like consider k to be to vary from minus infinity to 0, we assume this as a root locus. This is a
Mm-hmm.
common practice.
Okay.
We won't change k from minus infinity to infinity. That's what you have to consider here. K always varies from 0 to infinity. So k is always greater than 0. So for that values, for is it for stable for all values of k? It is true. Yes.
Okay. Okay.
Okay, fine. We'll move towards the next thing. What I
Mm-hmm.
was thank you. What I was telling is for quiz 2, you will be having a syllabus from week 5 to week 8, where week 5 covers PID controllers, week 6 covers this one, RH criteria, and also root locus. Both are equally important. And week 8 covers Nyquist and Bode. Oh, 7 I left, right? Oh, 7 covers Nyquist and Bode. 8 covers maybe lag lead compensators, I think. I'm not sure. I have to check. Wait. What is in week 8? Design using lag lead compensator. Okay. Here, this week 8 lag lead compensator won't be included for your quiz because this we are going to give it as a design assignment. So technically, you will have 3 weeks of problems, week 5, 6, 7 to cover for the quiz too. So you can score well if you practice it properly. But these 3 weeks are very difficult compared to previous 4 weeks. 4 weeks are the introduction and the base setting for the control systems. This actual fight six
Yes,
seven,
ma'am. Root
uh,
locus is very tough
yeah.
to understand.
So you have to sit and you have to practice each and every rule by yourself. Please don't open your books one day before the exam. Practice it well and do your quiz too properly. If you have any doubts, put it in discourse or ask in live session. Please join live session. Those who are watching the recorded or video also join live session. Practice problem before comes here and ask your doubts. Okay, this will boost your overall grades much. So please focus on this quiz too. Okay, right. Back to our week problem. Now I'm going to touch a little upon frequency responses and Nyquist today. Tomorrow or Wednesday, we will be seeing Bode plots. Okay. First of all, I want to give some introduction because most of you are not following your lecture properly. I don't know why. If you see that lecture and comes here to for the live session, it will be beneficial for you. Fine. So we'll start with the frequency response. Until week 6, we have seen everything using time domain analysis or time domain responses. Now we are switching into the different similar representation from week 7. It's going to be on the frequency response. It's opposite to the time response or your time domain analysis, right? So here the platform or the plot or the base you are trying or making your assumption will be different. Nothing else is different here. You used to consider T as a common parameter there. Now we are going to use omega instead of that. We are going to depend on the frequency, how the system is changing or the output is changing with respect to the change in the input frequency or change in the actual system's frequency. That's what we are going to study. It's a different domain study, but studying the same system as it is. That thing much difference, right? So, formally, how we define this frequency responses is frequency response of a system is defined as the steady state response. Steady state means after some time where it is going to settling, right? Steady state response of a system to a sinusoidal input signal. Why sinusoidal in particular means it was previously when they are discovering all these things, sinusoidal signal was very easy to generate and also it has all the changes from one point to another point steadily. It doesn't jump from here to here or here to here just like that. So it has a smooth transformation from one point to another point, and it is very much useful in studying the system parameters. So we are using sinusoidal input cycle, and you know the notion of sinusoidal inputs to a LTI system, right? This LTI system doesn't vary the sinusoidal input into any square form or triangle form. If you give an input to a LTI system as a sinusoidal, you will get the sinusoidal output just once. Just the frequency will be changed, right? There will not be any much changes to your input signal. So studying about a LTI system will be very easy when you use a sinusoidal signal as an input, right? So why particularly frequency response when compared to the time response means the data obtained from frequency response can often be used as a design purpose without any explicit mathematical model requirement, and also it enables mitigation of undesirable noise effects that seems to be very good in research, and it offers reliable solution for determination of transfer functions of LTE systems as I explained. So mathematically, how can we explain this frequency response in the sense your output response C of S is equal to G of S into R of S. Why it is G of S into R of S? Because C by R, that is output by input, is generally your transfer function, right? So the R has been taken here. This is equated to A omega divided by S square plus omega square, where omega is the frequency and A is the amplitude of the signal into G of S. This is how we define in the frequency response when compared to the time response. This can also be split into partial fractions and like K by S plus J omega plus K star into S minus J omega. We do all the inverse mapping plus all the partial fraction explanations, right? So at last we will get something similar to in the time domain. It is B sine omega t plus phi of omega, where this is representing your frequency and this represents your phase difference, where B is the A into G of j omega. It represents your magnitude or output amplitude. Amplitude, magnitude, everything is same. Magnitude is the mathematical quantity that represents the amplitudes, where phi of omega is your phase shifts, anything you can say, right? How can we relate the one we have studied so far with this frequency response? So far, what have been using? We are using S domain, right? We have been using S domain that in terms uses the Laplace transformation to formulate this S domain. So if I just substitute, S is a combination of sigma plus j omega. In general, we'll say this is sigma and this is j omega in a Laplace transform domain. But if you substitute S is equal to j omega by keeping sigma equal to 0, only the imaginary axis, then we derive this frequency response or frequency domain characteristics to make it little more simple. Okay, fine. There are many specifications. This needs to be explained properly. First one is resonant peak. So you can see all this content in your PPT also. Just I'm explaining it here so that we can do some problems based on this. So in time domain, if you remember, you can recollect like we have studied many time domain specifications, right? Peak time, rise time, settling time, peak overshoot, and what else? Delay time. So these are all the time domain specifications. Similarly, we have frequency domain specifications. Those includes resonant peak, resonant frequency, bandwidth, cutoff frequency, everything. So I will just briefly explain what and what about each and every specification. So resonant peak is the maximum value of your magnitude. That's it. Here the peak you used to get, no? For example, in time domain, if I have this, so this is my peak value. The time taken to reach this is the peak time, right? But here we are telling the same thing. If I have this as my omega, But this is the maximum peak. Then this represents your resonant peak. That is MR, the maximum value. Excuse me, of the magnitude M of j omega or A of j omega, anything, whatever system you are considered. Okay, this large peak here, the large the MR tells there is a large overshoot in your system. Similarly here, right? Both are same. There is no much difference. Just the name is a difference here. Second thing is resonant frequency. You would have known by this time, right? So the time taken to reach the peak is peak time. So the frequency that it takes to reach the resonant peak is resonant frequency. That's it. Time taken to reach M1. That's it. Sorry, not time, right? It's frequency taken. Frequency at which MR occurs. A little different based on your thing. If this is your resonant peak, then the frequency at which the resonant peak occurs is the resonant frequency. Third thing is bandwidth. It's little misleading because people use different explanation for bandwidth. In general, for this application, I will tell what we use. Okay, bandwidth is a frequency range, a range of frequency over which the magnitude m of j omega, I'm considering any system, stays within 70.7% of, or in quantity, it is 3 decibels of its zero frequency value. So, in time domain, just to compare it, we have studied that some 67.76 percentage to reach the final value we have studied, right? For example, if this is 100% value, then the time taken for it to reach the 67 some percentage, so that we call it as rise time, because it is depending on the time constant tau of your system, first order or second order system. Similarly, we have defined this bandwidth to be the 3 decibels. The frequency before it reaches 3 decibels, that range we call it as bandwidth. So this is important because this tells the transient properties of your system in frequency domain, not time domain. Okay. The fourth is cutoff frequency. We call this as omega C. This can also be called by omega B or BW. Both are same. So here the cutoff frequency is the specific frequency where your magnitude m of j omega drops to 1 by root 2 times of its zeroth frequency value. Where the zeroth frequency happening, where it is starting. Maybe it can start at zeros. Can here the frequency can start at 10 per minus 1, 10 per 1, anything. So from here, what frequency at what frequency the magnitude is reaching 1 by root 2 times of the overall magnitude, that is called as cutoff frequency. Fifth one is cutoff rate. The slope, its rate means rate of change of rate. So instead of doing one frequency, we are looking for the rate of change of this cutoff frequency. That's it. Okay. In time domain, frequency domain. In time domain, how we used to represent omega square divided by s square plus 2 zeta omega ns plus omega n square, right? Here, this is same, but we will just substitute wherever there is s, omega square. To differentiate this omega and that omega, I am taking this as omega and natural square, omega square. This will be j omega square plus 2 zeta j omega, sorry, omega n as it is, j omega plus omega n square. Okay. If you, this is what the difference between time domain to frequency domain. So if you find this, this is consider this as m of s. This will be m of j omega, replacing s with j omega. So we will get m of j omega will be omega n square divided by omega n square minus omega square plus j 2 zeta omega n omega. If you simplify this, you will get this. Right? So whatever we have defined before, we can get it in terms of mathematical quantity for resonant peak. From this, you can define the resonant peak of a system. The resonant peak MR can be written as 2 zeta root of 1 minus zeta square. Okay. Similarly, how you studied the TP, TR, TS, like 4 by zeta omega n. So we are studying the mathematical equation of each and every specifications here. That is, MR is the resonant peak. I have defined what and what before. So just giving you a mathematical equation. Then resonant frequency omega r, that is equal to similar to whatever we have before. Omega n. There in time domain, this is omega d, right? Now here it is omega r. That's it. And bandwidth can be represented using omega b.
Ma'am,
Yeah.
resonant frequency omega here equal to omega in root over 1 minus 2 zeta square.
Okay. Okay. Yeah. 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 Yes. Sorry. Sorry. Yeah. That's right. It's 2 jitters. I'm sorry. Just make this change. Whereas in time domain, this will be omega d equal to omega n root of 1 minus zeta square only.
Yes, ma'am.
Okay. Now the bandwidth is little complicated, a little long free formula. This will be 1 minus 2 zeta square plus 1 minus 2 zeta square plus root of 4 zeta power 4 minus 4 zeta square plus 2. Please don't worry about this formula because most of the times we won't use this formula. We will get it from the graph itself. So don't worry about this formula. Okay. Just remember, try to remember this formula if you can. Most of the times we won't use this. Okay. Now just it's little comparison because you are familiar with time domain. I want to teach this through time domain. Teach this frequency through the time domain. Now the difference or the similarities between time versus frequency. If we consider that zeta is very low, there are these are the criteria I'm considering. And with respect to the bandwidth, these are the three criteria I want to tell. So in time domain, if the zeta is low, what it represents? For example, zeta varies from 0 to what happens? Okay. Zeta varies from 0 to 1 for our interest region, right? So only you will get the overshoot and all. Otherwise, if it is less than 0, there will not be any damping. There will be sustained oscillations, zigzag, zigzag. And if it is greater than 1, it will be very slow. It's like very slowly moving. Both are not interested. So for low values of zeta, what it will you will get, you will have a good peak, like larger peak. For high values of zeta, you will get smoother. There will not be any much bigger peak. As it reaches 1, you will get the critically damped nature, right? So as zeta is low, there will be oscillations will also be low. Similarly, here also we will get a flattened curve for a low zeta values in frequency domains also. For high zeta, you will get a smoother response, but a slower settling time, right? There you will get a sharp curve or a sharp resonant peak, similar to the time domain. Both are nearly equal. In terms of bandwidth, small bandwidth implies slower response. Here, larger bandwidth implies faster response.
Ma'am,
Slower,
in lower zeta, it is given that higher oscillations.
When we have for zeta equal to 1, you have this, right? There, it is critically damped. There will not be any oscillations. As it reaches higher zeta values, there will not be any oscillations. When the zeta is less than 0, then it will become a sustained oscillation. Here only there will be oscillations, right? By physical meaning, if you see. Okay, maybe I will check and get back to this concept. I might be wrong here also. If it is given in the PPT, I will check and come back. Okay. The thing is, there will not be any difference between time and frequency domain. That I want to make sure here. Whatever the way the time domain system behaves, frequency domain also it will behave similar to that, because this is not changing from one form to another form. This is just a different representation of the same system. That's it. Okay. That you take away from this table. Fine. Okay. We will solve few problems based on this formula. Oh, one thing I missed. This we learned, no? This exists only if zeta is less than 0.707. Or that it will become unstable. Okay, that is one thing. And we'll solve problems. First one, okay. Determine. Okay, let me open and close and open. It's become lag. Determine the steady state response of g of s equal to 10 by s plus 2 for an input r of t equal to 5 into sine 3t. Okay, the input is 5 sine 3t, where 5 is the amplitude, 3 is the frequency. That's how we mentioned, right? A sine omega t, A magnitude, omega is the frequency. And the transfer function they have given 10 divided by s plus 2. So for a frequency domain characteristic, how we used to represent this? How we used to represent this? First, identify the frequency. First step is to identify the frequency. The frequency omega equal to 3 here as given in the input. Second is replace s with j omega. This will become 10 divided by j omega plus 2. Third is to calculate the magnitude g of j omega. How do you calculate the magnitude of the system? How do you calculate for any complex variable? For example, if this is your complex variable, then it will become root of a square plus b square, right? Similarly, for this system, this will be 10 divided by root of 2 square plus what is omega? G3. 3 square. So this will become 10 by j3 plus 2, substituting omega here. So this will become 2 square plus 3 square. What is 2 square plus 3 square? 2 square is 4, 9, 13. 10 by root 13 is your answer for your magnitude. Magnitude of your system is 10 by root 13. You can write it in decimal also. And the next step is to calculate the phase. Calculating phase will be g of j omega. That will give me for a system of some k by a plus bj, my angle will be, this will be 0. For this, it will be minus of tan inverse of 0 minus tan inverse of b by a, right? So if I want to write the same thing here, it will be 0 minus, because there is no complex here, right? For a real system, the phase shift will be 0. Ayyo. tan inverse of b by a means b is here is 3. 3 by 2. Please be careful while writing this. Some people will write 2 plus 3j, then they will write 2 by 3. Always complex b will come above. The one coefficient near the j term will come above, and the other one real part will come below. So this will become minus tan inverse of 3 by 2 would be 1.5. Whatever value you can calculate that with calculator. The results, next thing is to write it as a combined form. That is the result. C of t is equal to your A and magnitude of g of j omega sine omega t minus your phase shift. So how to write this? What is A here? From here, A is 5. 5 is your A, right? Capital A, magnitude 5. G of j omega is this one. This is g of j omega. 10 by root 13 sine omega t. What is omega here? Omega is 3t. So 3t minus whatever value you found from the tan inverse of something. I'm just going to write it as it is. Minus tan inverse of 1.5. Just calculate the value and put it here. This is your output in terms of time domain. So now you have converted S domain to time domain using frequency response analysis, or whatever you can say, frequency response technique. Right. In time domain, what we would have done from C of S to C of T, we would have taken a Laplace inverse or partial fraction and Laplace inverse, right? To get the C of T from the C of S. Here we use this magnitude and phase formula to find the same thing. Right. Problem 2. Now we'll use the formula we learned before. They are giving a system has a natural frequency omega n equal to 5 radians per second. If they have given units in the question, try to write with units. Tau equal to zero point 0.5, because sometimes your questions will have same number but different units. So please study along with the units. Your tau is 0.5. You're asked to calculate the MR and omega. MR is the resonant peak and omega is your resonant frequency. What is a formula for MR? MR is here 1 by 2 zeta 1 minus zeta square. Everything is available here. Just zeta in your question. For omega R, you need omega n and zeta. Both are available. Just substitute here in that formula and you will get the answer. We will do that by hand. MR equal to 1 by 2 zeta root of 1 minus zeta square. 2 into 0.5 root of 1 minus 0.5 square. 1 by 2 into 0.5 to root of 1 minus 0.25. 2 into 0.51 root of 0.75. I don't know what is root of 0.75. 0.86 something. 1 by 0.866 something. So 1 by 0.866. 1.154. This is your resonant peak. Whereas your resonant frequency can be given by omega n root of 1 minus 2 zeta square. Omega n is given as 5 root of 1 minus 2 into 0.5. 5 1 minus 1, that is 0. Oh, how come resonant frequency is 0? So a square it is there, no? So 2 into 0.25 it is. So again 0.5, 5 into 0.5, root 0.5 is what I have asked. That's it. MR. Apart from this, what could be asked? Bandwidth is too much. You we won't ask you to use that formula. Okay. With this introduction, I guess it's easy to understand. I will see if I have some other problems. This is compensators problem. Okay, we'll go to Nyquist problem then. Do you have any doubt in this frequency response introduction? Why, how, anything? Okay, fine. We'll move to frequency response, sorry, Nyquist problem. So, similar to root locus in your time domain, Nyquist and Bode plays a very major role in frequency domain analysis. So first we will see Nyquist today, and about Bode we will do on Wednesday. So why do we actually do this Nyquist? We want to understand the response of a system to varying frequency input. This is the primary motivation, I would say, for doing this. While time domain methods describe immediate reactions, this frequency domain reveals long term behavior of your system characteristics and stability concepts. So, if I want to see more towards stability, I will look into this kind of analysis for a longer period of run, not immediate run. Okay. So, this Nyquist plot will serve as an extension of frequency response characteristics, what we do till now. This depicts the entire frequency range from 0 to infinity as we do in root locus. Here we are changing omega instead of k in a single vector based representation. That's what the main motive behind this is. For example, in root locus, you vary k from 0 to infinity and plot the locus of that of your system. Here in Nyquist, you are going to change omega from 0 to infinity and going to plot the same locus, you can say. Otherwise, I'm going to trace the poles of the system for a change in frequency from 0 to infinity. So for lower frequency, you will analyze for lower frequency how my system will behave. For high frequency, how my system will behave. Based on this, I can comment on the stability of my system in a long run. That's what the whole idea behind doing this Nyquist plot. It's just a immediate analysis that you don't have to rely on the system for a very long time, but still you can say at this frequency the system will be stable. At this frequency the system is tend to go from stability to the verge of instability. That kind of analysis you can do using this Nyquist stability criteria. So there is a rule called mapping rule, which is very important in Nyquist criterion. It's inside topic. Inside the Nyquist criterion, I'm saying there is a mapping rule. For example, how do you usually explain your system? For if I give this as an input, that is R of s, G of s is my system transfer function, C of s is my output. I'm considering a closed loop system, that is minus. So closed loop system representation can be given as G divided by 1 plus G of s into H of s. Considering H to be 1, I won't have this G of s by 1 plus G of s. So here, which one is uh, telling the stability aspects of a system? Is it a zero or the pole? Which one tells you about the stability nature of the system?
Pole, ma'am.
Pole. So we will be concentrating on this more than the numerator when speaking about the stability. So this, if we equate it to zero, we call this as a characteristic equation. Why we are equating it to zero? Then only we will know the poles or roots and poles are same for us for any system in time domain and frequency domain anywhere, right? So this is when we will know the poles of a system. So we call this as a important criteria to analyze the system stability. So here I am not going to assume hs equal to 1. Instead, I'm going to put hs as it is for a generalized representation of any system. So here, this characteristic equation plays an important role. I'm going to call this entire thing as Q of S so that it will be easy for me to explain. Right. So this Nyquist criterion tells a function Q of S, which is this entire term, the characteristic equation of a function that is called as Q of S. Q of S maps a contour. Contour means a diagram, just like a trace of points. That is a contour. Maps a contour in S plane to a corresponding contour in QS plane. So what basically what the Nyquist people are telling, so it's like a in a general or funny way, if you want to say, people who make films nowadays, maybe I'm not very much into that. They have some high reality films have this assumption that we are having a multi-dimensional universe, like multi-universe concept, where everything is happening parallelly. Whatever happens here may affect that instances. There are many theories like butterfly efforts and all. So similar to that, they are defining one thing. We are calling this as a S plane, and I'm going to call another thing as a QS plane. I don't know how this plane is going to look like, but whatever they are saying is, so if we have a contour around here, sorry, not like this. If I have a pole and a zero, anything, I have two poles or any zero, I'm starting with one pole, one zero. So if I do a contour around this pole or zero, please note it is not and, it can be one pole, two pole alone, or one pole, one zero alone. Any combination would be fine. But if I make a contour, like a trace of points around the poles or zeros in S plane, they are believing that it is going to happen on the QS plane also around the origin. That's what the idea behind Nyquist plotters. It's like mere approximation, or you can say projecting from one plane to another plane. Okay. So if you do one thing here, it will happen here also. That's what the theory says in Nyquist plot. So how changing the direction of the contour, or how changing about where we are rotating in the contour, will change the contour in the QS plane also. This is going to affect it. So what is our QS? Our QS is this 1 plus G of S into H of S, right? So they are saying if a contour in S plane J omega zeta, in the contour in S plane encircles zeros and poles The corresponding contour in the QS plane encircle the origin n times QS plane. So if a contour rotates a zero or a pole in S plane in clockwise, maybe it will rotate again in the around the origin in terms of n equal to p minus z. N equal to p minus z, where n is here is the number of counterclockwise direction or encirclements. Okay. P is the number of poles in open loop. Very important it is. Z is the number of zeros in open loop system. Fine. Now they are saying, for example, if I have one, how to say, if I have let's take it easy. If I have one pole here, if I rotate it or make a contour in a clockwise direction one times, then in the QS plane, this will make a one contour in a clockwise direction about the origin. That's what they are saying. From this, you can find the
Ma'am, in
step.
S it is anti-clockwise.
Yeah, this is anti-clockwise, counterclockwise.
Yeah. And then in QS that is clockwise.
Yeah. And that is, this relation can be given using the equation n is equal to p minus z, where p is your open loop poles and z is your open loop zeros. So if I have two poles in my system and one zero, so 2 minus 1, there will be one counterclockwise direction contour would have happened in my S plane. That's what it is. Is it clear? So if there is one counterclockwise direction, the P and Z will be stabilized based on that. If I have two counterclockwise directions, this I can say there are two poles and zero zeros. That's how it changes. So if I give two information without only
I
one
don't
information,
understand clockwise and anti-clockwise. That is counter and
okay,
clockwise and
count,
anti-clockwise. Please explain that.
counterclockwise is equal to anti-clockwise. This direction. Both are same. We can use interchangeably. Clockwise is only one, only clockwise this way. Both
So, ma'am,
counterclockwise and
when it will appear at happens at counterclockwise and when it will be clockwise.
okay, wait. Wait, I will explain it with the problem. It will be easy for. Yeah. Control weak sound. If you see this line. As S moves along the Nyquist contour, a closed contour is traversed in QS, which encloses the origin n equal to p minus z times the counterclockwise direction. For example, this in the Q of S, if you have a encirclement in counterclockwise direction, this will be equal to your n. So if this counterclockwise it has encircled in 2 times, then your n equal to 2. It is equal to your P minus Z, where P is a open loop pole and Z is your open loop zeros. So this two will be equal. So number of times your P minus Z is the encirclement in your QS in counterclockwise direction. That's what this equation tells.
Two means two times it
Two
will.
times it rotated in a counterclockwise direction.
Okay, ma'am.
If it is rotated one time clockwise, one time anti-clockwise, then it will be nullified.
Okay, ma'am. Now I understood.
Okay, fine.
Yes.
Right. So there is a when I explain this, I want to use this Nyquist criterion. I said that we are majorly depending are majorly finding stability based on this, right? So there is a separate criterion based on this Nyquist plot that we call it as Nyquist stability criterion. This is also one of the important concepts in this. This criterion tells how do you find the stability. For example, if I have an open loop system, how do we usually find the stability? Open loop system means only G of S. First, we will find the G of S by 1 plus G of S into H of S in terms of closed loop system. We call this as closed loop transfer function. This open loop transfer function, OLTF. We will find this, then we equate this to 0 to find the poles, and based on the location of the poles, whether it located in the LHS, we call the system is stable. Otherwise, the system is unstable. This is the procedure we used to do so far to find the stability. But the Nyquist stability criterion tells with only the open loop transfer function and the Nyquist plot of the open loop transfer function, you will be able to tell whether the closed loop system is stable or not. This is this is easy, right? If we have some tools like this in our hand, you don't need to go through all this headache to find the closed loop system and equating poles to 0 and all to find the stability. From this open loop system and the Nyquist plot, if I plot it, then that itself will be enough for me to say, tell whether my closed loop system is stable or not. How can we do that? So this means for the closed loop system to be stable, the number of counterclockwise encirclement of the origin Q of S should be equal to the number of right half S-plane poles of the Q of S. So if I have one encirclement, they are saying if the open loop transfer function has one right half S-plane poles, that is unstable pole, then this is okay. This will be equalized. So my closed loop transfer function will be stable. Let me explain it here. So if I have Q of S, one encirclement of counterclockwise direction, then in my open loop transfer function, I have one open loop pole, sorry, in the right half of the S plane. S minus A means S is equal to A plus right half S plane. In general, this is unstable, right, in open loop system. If a system with open loop pole in right half of the S plane gives one counterclockwise encirclement in Q of S, then my closed loop transfer function will be stable. That's what this Nyquist criterion tells. For example, my open loop transfer function lies here 2. If I plot my transfer function, Nyquist plot of this transfer function, if I get one encirclement around the origin counterclockwise n, then my closed loop system transfer function will be stable. That's what my Nyquist stability criterion tells. So with this knowledge, you will be able to tell your closed loop system is stable or not. That's the whole point in doing this. I want exit to. Mm. That's what this criterion tells. Okay, there are open loop unstable poles of the system. If the open loop system is stable, the closed loop system is stable. If n equal to p equal to 0, same thing. If you put this in the formula, this will be proved. So now we know the stability criterion. The next thing is how to draw this Nyquist plot. That is the next point we are going to learn. So since we overshoot time, we will put this in the next plot. So I will tell how to draw the Nyquist plot, and from there, how to find the stability of the system. with an straight away to the problem. I won't explain this next time, and then we will do the board explanation with along with the problems. And here, the important thing is you can do this in MATLAB in very easy single step. For example, in MATLAB, if I save a system, I'm saving a system transfer function one as 1 by s plus 1. So how can I write it? 1, 1, 1. Because this loosely translates to 1 by s plus 1. Coefficient of s, coefficient of constant. So I can say R locus of transfer function 1 will give me root locus straight away. A Nyquist of transfer function 1 will plot the Nyquist plot. You don't have to trace it by hand. But this is very easy in the system, but in real time by using hand without any computer, how can we plot this and how to interpret from those plots? How can we use this as an analysis tool and everything we are studying here? Okay. So practice this before coming tomorrow, sorry, for Wednesday, and then we can solve some problems in the MATLAB also. This will be useful for you in the design assignment problems.
Ma'am, I can't understand how this graph is drawn.
This is what we are going to study in the next week. How to draw this graph.
Okay, ma'am. Okay.
I'm saying in MATLAB, this is easy. The previous week you studied is confined within this one line, R locus. If you put R locus and transfer function, you will get the root locus. In MATLAB, if you type Nyquist and your transfer function, if you give your transfer function, you will get this plot as it is. But by hand, how can we plot it? That's we are going to see the next time.
Okay, ma'am. Okay.
Fine. Okay. We'll wind up this session. Um, I'll solve problems of Nyquist and Bode in the next session. If you have any doubt in previous GE or anything, stay back here and ask. Otherwise, you can leave.
Ma'am, in this week, that is quiz whole lecture, you after Wednesday session, I will ask you. Week 7, there is a question in graded assignment. It is
Week,
tough to
week
this week.
seven,
Week 7, yes, yes, week 7.
you're saying it's tough to solve.
Yes, ma'am. I can't understand that question.
Okay. Week 7 is Nyquist only. This one only, whatever we are seeing. But yesterday is the deadline for it.
Yes, yes.
Okay, we'll see. We'll see. We'll solve those problems Wednesday
Okay,
also.
okay, ma'am. Okay, ma'am.
Mm.
Okay.
Thank you. Thank you.
Thank you, ma'am.
Thank you.